In this lesson, we're using the distance formula in order to find perimeter and area of figures. And I'm going to have to kind of go through a few things quickly. For example, you'll notice in the first example in the lesson, they gave you the coordinates of A, B, C, D, and E, which you see I have already plotted and connected the dots. In part B, we are asked, are there any sides for which we would not need to use the distance formula since the instructions are asking to find the perimeter? I would not have to use the distance formula for segment AB. It's a horizontal segment. Which means you can just count the spaces. It is 5 units long. And then they want you to use the distance formula to find the remaining 4 side lengths. And then you would add them together in order to find the perimeter. In the interest of time and the fact that I have a similar problem later in the lesson, I'm not going to do that. I'm just going to move on from here. So perimeter, you know, is finding the sum of all of the side lengths. You would use distance formula and then you'd add everything up. Area involves formulas such as what you see on the screen. And the assumption is in the textbook that you've seen most, if not all, of these formulas before in middle school. These might be what I would consider to be new to some of you. But if you could consider a rhombus and a kite as being broken down into triangles, you could still work the problem out. All right. In example 1, part A, they're finding the area of the figure. Now, I'm not terribly fond about the way that they did this. I'm going to show you later on in the video how to use subtraction to find the area of a figure, and I think that you would find that to be a lot more intuitive and easy than the process that they've used here. They're using the fact that the area of a triangle is 1/2 base times height. And one thing that I'm not terribly fond of is they found the point D, -1, -1, and they say it appears to be perpendicular to the base of AC, and then they use the slope formula to show that yes, they are, but they're kind of assuming that every problem that you're going to have is going to be just as easy to kind of eyeball your way through finding a perpendicular segment. And I know that that's going to be a challenge for some of you. So once again, the method that I show you later on using subtraction might be an easier method for a problem like this. In example 1, part B, you're finding the area of this quadrilateral, DEFG. And they say, again, I'm not terribly fond about the way that they're doing this. They say it appears to be a rectangle, and they are using the slopes of all 4 sides to show that it is a rectangle. So that's not too objectionable. DE, the slope of DE is 3 minus 6 over the 4 minus -2 they already have set up there. So that's -3 over 6, which is -1/2. The slope of EF is -1 minus 3 over 2 minus 4. When I simplify that, I have -4 over -2, which is +2. So hopefully you're noticing that DE and EF are, in fact, opposite reciprocals. Let's continue. FG, its slope is 2 minus -1 over -4 minus 2. So that's 3 over -6, which is also -1/2. Still looking good for this to be a rectangle. Finally, the slope of DG is 2 minus 6 over -4 minus -2. So that's -4 over -2, which is 2. So DEFG is in fact a rectangle. And since the area of a rectangle is base times height, I'm just going to find the lengths of 2 consecutive sides and in order to find the base and height of this rectangle. So the length of FG is 2 minus -4 quantity squared plus -1 minus 2 quantity squared. So I've got 6 in the first parenthesis. Squared is 36. In the second parenthesis, I have -3 squared, which is 9. So 36 plus 9 is 45. And what they're wanting you to start doing is simplifying your radicals whenever possible. And what that means is you're dividing away any perfect square factors. So what numbers are perfect squares? 4, 9, 16, 25. And they're perfect squares because 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. So 45 is divisible by 9, so I'm going to break that 45 down into radical 9 times radical 5. But you know that the square root of 9 is 3, so the length of FG is 3 radical 5. Now finding the length of GD, that is -2 minus -4 squared plus 6 minus 2 quantity squared. So in the first parenthesis I have 2 squared, which is 4. In the second parenthesis I have 4 squared, which is 16. 4 plus 16 is 20. That 20 is divisible by 4, which is a perfect square. And when I take the square root of that 4, I get 2, and I still have that radical 5. So the area of DEFG is base times height, which is 3 radical 5 times 2 radical 5. And I'm going to go step by step on this. 2 times 3 is 6. Radical 5 times radical 5 is radical 25, but the square root of 25 is 5. And when you multiply that 5 times this 6, your answer is 30. In part B, why was it necessary to find the slopes of these sides? The area of a rectangle is base times height, and in a rectangle, the base and height are the sides. So if I hadn't been able to show that this was a rectangle, I would have had to find a height for the parallelogram. So in part B, why was it necessary to find the slopes of the sides? To show that it was a rectangle, allowing us to use consecutive sides as the base and height, as the B and H. A composite figure, as you see, is made up of smaller shapes. So we can take a figure and break it up into triangles, rectangles, and parallelograms, find the areas of those figures, add those areas, and that will give us the area of the composite figure. So you'll see that they did that in example 2. They broke pentagon ABCDE up into 3 triangles and a rectangle, found the area of those 4 pieces, added them together in order to find the area of ABCDE. And we're going to do that here. Again, I'm trying to speed up the process a little bit without slowing my video down. I've already identified the coordinates of the points, as you can see on the right side of your screen. And so we're going to take PQRST and break it up into smaller pieces. They're already telling us, go ahead and break it up into a triangle and a parallelogram. Now it says triangle PQT appears to be a right triangle, so let's check that PT and QT are perpendicular. So the slope of PT is 1 minus 4 over -3 minus negative 4. That becomes negative 3 over 1, which is just negative 3. The slope of QT is 1 minus 3 over negative 3 minus 3. So that's negative 2 over negative 6, which reduces to 1/3. So those are opposite reciprocal slopes, which means triangle PQT is a right triangle with base PT and height QT. So let's find the lengths of those two segments and use them in the formula that they have here. Area of a triangle equals 1/2 base times height. So we're going to find the length of PT, that's negative 3 minus negative 4 quantity squared, plus 1 minus 4 quantity squared. And the first parenthesis, I have 1, squared is 1. Second parenthesis, I have negative 3, squared is 9, 1 plus 9 is 10. The length of segment QT is negative 3 minus 3 quantity squared plus 1 minus 3 quantity squared. So in the first parenthesis, I have negative 6 squared, which is 36. Second parenthesis, I have negative 2 squared, which is 4. That gives me square root of 40. 40 is divisible by 4, so I'm going to break the 40 down into square root of 4 times the square root of 10. You should know, however, that the square root of 4 is 2. So that means that the length of QT is 2 radical 10. So the area of triangle PQT is 1/2 base times height, so that's 1/2 radical 10 times 2 radical 10. This 1/2 and 2 cancel each other out. Square root of 10 times square root of 10 is square root of 100, which is just 10. Next, we're going to verify that QRST is, in fact, a parallelogram. Well, we know that QR and TS are parallel since those are both vertical sides. Notice them in the diagram. QR and ST are vertical segments. So we know that they're parallel. And we already found the slope of QT. Let's compare it to the slope of SR. So the slope of SR is negative 1 minus 1 over negative 3 minus 3. So that's negative 2 over negative 6, which is positive 1/3, which is, in fact, the same as the slope of QT. So QT and SR are parallel, so this is a parallelogram. And then your book does something that I don't agree with. First of all, it's got this dreadful typo here. This is not a triangle, it's a parallelogram, QRST. RT is an altitude of it. It's the height of it. If I look at it sideways, I could treat ST like a base of the parallelogram, and RT would therefore be its altitude. And it's a horizontal segment, so that makes it easy to count the spaces for. Area of a parallelogram is base times height. As I said before, we're going to treat ST like a base of the parallelogram, and that is 2 units long, times the height of the parallelogram is the length of the altitude RT. That's another segment that we can just count the spaces for. It is 6. And so that's 12. So the area of PQRST is equal to the area of the triangle, which we found here, plus the area of the parallelogram, which we found there. So it's 22. This is the method that I was talking about earlier, finding the area of a figure by subtraction. In order to subtract something, I must have the area of something bigger. So what they're wanting you to do is enclose the given shape in a larger rectangle. Because rectangles are easy to find the area of. Let's call this rectangle ABCD. Area of the rectangle is base times height. And the base of ABCD is the length of DC, which I can count the spaces for. It is 7. The height of this rectangle is the length of BC, which is also something I can count the spaces for. That is 9. So the area of the rectangle is 63. And then I'm going to subtract away from it all of these triangles that I have kind of accidentally, if you will, enclosed. Right? So I'm going to find the area of triangle AWZ. Area of triangle is 1/2 base times height, so that's going to be 1/2. Well, the base of AWZ could be the segment AW, which is 2. And the height of triangle AWZ would be the length of segment AZ, which is 6. So triangle AWZ has an area of 6 square units. Next, I'm going to find the area of triangle WBX. Same formula, 1/2 base times height. The base of triangle WBX is the length of WB, which is 5. The height of triangle WBX is the length of BX, which is also 5. So this is 12.5. Find the area of triangle XCY. That's 1/2 base times height again. The base of triangle XCY is the length of segment CY. It is 4. The height of triangle XCY is segment XC, which is also 4. So that area is 8. Finally, area of triangle DZY is 1/2 base times height. The base of triangle DZY is segment DY, which is 3. The height of triangle DZY is the length of segment DZ, which is also 3. So that's 4.5. So I'm going to add up all these triangles. So area of the triangles. And in my calculator, I add these all up, and I get 6 plus 12.5 plus 8 plus 4.5, and that's 31. The area of WXYZ equals the area of ABCD, my rectangle there, minus the area of the triangles. So that is 63 minus 31, which is 32 square units. So sometimes that is a very useful strategy when you're dealing with a strange figure.